So we have already discussed about how to find the global minimum in the previous lecture. Let's revise a little bit and let's continue with our lecture. So here we can see if we plot the sum of squared error, which is nothing but our error. So if we plot the graph of error with respect to this omega naught and omega 1, which is nothing but our y-intercept and our slope. So if we plot the graph with taking just different values of this x and y and omega naught and omega 1, you will see some graphs like this convex curve. So this convex curve, you will just find it, and our main goal is to find this lowest where we have the minimum sum of squared error. So this is a sum of squared error curve, and here at this point, which is right at this curve, you can see the minimum value in this curve will be at this point. You won't have here, you won't have here, and here also. So this is an optimal solution basically. You might have, if you just take a point like over here and here, if you just take a point at these two, then you'll see which point will have the minimum. So in the case of these 2 points, obviously this red is optimal solution. If you have to take basically based on these points, let's imagine we don't have this global minimum and you have to take the decision based on these 2 points, then obviously you will take this red, because this red has minimum, that is lowest among these two. It has the minimum sum of squared error. So we just don't want this error to be maximum in our project, so that means we just make this as minimum as possible, and the minimum is at this point, which is our global minimum. So our main goal is to find this global minimum. Now in order to find this global minimum and everything, what we need to do is we need to basically know one concept, which is partial derivative concept. So here what we are going to do is I'm just going to give you some idea here. So I'll just say I'm not going to write any fancy these terms that we have been learning like this yi and omega naught and omega 1, although this is what we will be needing in a moment, but let's get a good concept and then we will go in that equation. So this is observed value, this is observed value, so I'll just say this is observed, and similarly for the predicted value I'll just say minus predicted, and this is whole square, and this is nothing but our error. So this is a next way of saying sum of squared error, and for each every data points we have a summation. We have to just do the same task for each and every data points. So this is all about the error. And another form of writing this equation is right here, which yi is observed, and you can see fxi is nothing but this fxi is a predicted value, which is our just a straight line. So we just represent it with omega naught and omega 1, which is nothing but saying this prediction was our straight line in the case of linear regression. So linear regression is going to create this straight line. So this the straight line equation is nothing but y equal mx plus c, and this is our prediction. And whenever this is a prediction, the m will be represented as omega 1. I'll just represent it omega 1, and c will be omega naught, and just represent this and just put it in the place of p. You will get that value. Now let's go over here and let's do something that is related to partial derivative. So why do we need this partial derivative is a concept over here. So in the local minimum, if I just again plot the graph, and at this not at this global minimum where sum of squared error is minimum, the curve, the slope of this curve, so the slope of our curve, which is nothing but the slope of this SSC, because this is the curve of a SSC. So that means the slope will be of the SSC will be 0. So now if we find the slope of this equation, if we find the slope of this equation, and if we make it as a 0, then we are going to find this global minimum point, which is our main goal. So now how to find the slope of this curve, or how to find the slope of this equation, which is right here, the equation of this. So how to find the slope? So if you want to find the slope, so slope, the formula of the slope is you have to take the partial derivative with respect to this x's. So x's here is nothing but this omega naught and omega 1. So you have to take the partial derivative with respect to omega naught at first, and then you have to take the partial derivative with respect to omega 1. So this way, this is nothing but a way of saying it is a slope. So slope is the partial derivative of that function, or basically small change in your curve. So slope is a small change. That is the equation. We can also say it is a rise by run. So it is just a small change on your graph, which is given by this partial derivative. So a small change is represented by this partial derivative. And similarly, we do it for omega 1. And if we just assign this as a 0, then we find this global minimum point. And now, if I show you in the equation, this was sum of squared error. If we do the partial derivative of it, let's see. If I do the partial derivative, let me just take an example over here. Let me just write this same equation in our this whiteboard, and we are going to compute it, partial derivative. Let's compute it from the scratch, and let's see what we are going to get the equation. So let's write that equation where we are going to compute the value of SSE with respect to omega naught. First, let's do it with respect to omega naught, and then we'll do with respect to omega 1. So what is the equation of SSE? So that is observed minus predicted. So I'm just going to write yi for the observed minus predicted. So predicted is nothing but this fxi. So fxi is something that is an equation, which is y equal mx plus c. So the value of m is nothing but, I'll just say, omega naught plus omega 1 x. So this omega naught is a c, omega 1 is the value of m. C is a constant, m is a slope. So let's write this equation in the case of fxi. So if I say fxi over here, so let's do the partial derivative, and here we have the square because this sum of square residual, and let's do with respect to omega naught. Now if I represent this fxi with this equation, then this equation becomes, that is, let's do it over here, yi minus, and this equation minus omega naught, and this minus will make this plus also the minus, and that will be omega 1 x. And let's take a square of it with respect to omega naught. So here, now it's time to take a partial differentiation. So first of all, let's see what is a partial differentiation. So partial differentiation is basically, let's take example over here. I'll just give you example. So how we can compute the partial differentiation? Let's see. So I'm going to do partial derivative of this p square. I'm going to do the partial derivative of this p square of function basically with respect to j or z. So this is not valid. You can't do this partial differentiation, because if you want to do the partial derivative with respect to that parameter, then this j should be in some existence with this p. So you can do something like this. If there is z square with respect to z, then you can do it, because this j existence is over here. So this j existence is over there, but this z and p are quite different. If you have something like this, let me take another example like here. If you have here, let's say you want to do partial derivative of p square minus q square with respect to, let's say, p. Now you can see this p has the partial that is relative with this equation, because we have here p and here q. So we can't do this part, we can't do with respect to p, but this part has this p square. So for this part, for this q square part, this is basically considered as a constant, and whenever you do the derivative of constant, it will come as 0. So let's do the partial derivative one by one. So I'll just take a simple example where we are going to do the partial derivative of p square. So firstly, I have already told you the concept, which equation you can do the partial derivative and which not. So if I am doing the partial derivative of p square, if I am doing the partial derivative of this p square with respect to dz, then it is not valid, because we don't have this z any existence in our function fx. So there is nothing about z in our equation. But similarly, what if I say something like I am doing the partial derivative in this case with respect to p? Then obviously we have this p over here in the function, then this is valid. So this partial differentiation is valid, then we can do the partial differentiation of this equation. So how to do the partial differentiation? So in order to do partial differentiation, first of all, just go over here and in this case we have the existence of p, then we just do the derivative. So how to do the derivative of this p square? How to do the derivative of this p square is, first of all, in the power, whatever you have in the power, just slide it over. So just slide this down, just take this down. So we have 2, and just put the, that is our base over here. So base is p, and just do this power. In our case, the power should be subtracted with the 1. So this is our partial derivative, and it comes as 2p. So this is our partial derivative. So what we did was, in the power, whatever we have in the power, we will just drop this down. So whatever we have in the power is, we have 2. So we just drop that down over here. And we have the base over here, which is p. And now this power, whatever we had initially at the power, should be subtracted by 1. It is nothing but saying, if you just do the partial derivative of, let's say, an with respect to partial derivative of a, this is valid obviously because we have the existence of a in the numerator. So here what we can do is, first of all, just slide this n down, which is n, and just take a and do n minus 1. So this is a derivative of a to the power n. So just see here, this is the derivative, how to do the derivative. Now similarly, let's check out other derivative also, a simple derivative. We do not require any trigonometric derivative, like you should not read, like if you want to just broaden your knowledge, then just do derivative with respect to sine and cos, but we don't need that. For the entire course, we will be needing only the simple partial derivative, like the simple partial derivative, like how to do the partial derivative of this p square with respect to p, and so on. So similarly, you can do this. Now, I have already told you before here how to do the partial derivative. First of all, you have to make sure that whatever you have here in the, that is in the numerator, the function, the base of the numerator should has, so see here, the base of the numerator is nothing but this p. So you must have known by now this thing over here, and at the upper side we call this as a numerator, and this lower part we call it as a denominator. So it is denominator. And now whatever the base that we have at the numerator, so base is this p. So the existence of this p should be at the down. So you can say p is over there. So that means we can do the partial derivative of this. So first, just know about that. And second, if we have a function something like this, let's take example. If we have a function to do for the partial derivative, let's say p square minus q square with respect to p. So if you want to do the partial derivative of this, then you can clearly see in our case we have this p square, existence of p square over here. So we can do the partial derivative of this. But what if we have something like this z? So we can't do this again because this z, so nothing about z is referenced over there. So we can't do this about the z. So similarly, if we have something that is with respect to p, then what we can do is, for the p square, we can do the partial derivative with respect to p, obviously. We can do this partial derivative. But q, there is nothing about the q. So that means this q square will be regarded as a constant. And if you do the derivative of constant, then it will be always 0. Just remember that. So let's do with respect to p. Let's do the p square with respect to p first of all. So what is going to be p square with respect to p? What is the derivative of this? First of all, you slide this power down. So 2, and you just keep this, that is base, and just do this minus 1. So our value is 2p. And now our equation here will be 2p. And if you do, here is a minus, here is a minus, see here, and here is minus. And now let's do the q square with respect to p. Here the q square will be regarded as a constant. That means it will be 0. So our partial derivative of this equation is nothing but a 2p. So this way we find the partial derivative of any equation. See here, again if I do something like this, let's take an example. If I do something like, let's see, okay, if I do like p square minus q square with respect to q. So obviously we can do this because the existence of q is inside this function. You can see q square right there. So for this, with respect to q, the p square will be regarded as a constant, so the constant derivative will be 0. So p square is constant with respect to q. And similarly we have this minus after p square, and we do now for in the case of q. So for the case of q, we have q square. So let's do the derivative of q square with respect to q again, and that will be 2q. So now we do something like this, 2q, and our output will be minus 2q. So this is the way you do, that is partial derivative. Now let's do the partial derivative, the same concept in order to, so why do we need to take the partial derivative? Because we need to calculate the slope. So that is the main thing that we need to calculate over here. So why did we learn the partial derivative? Because we need to find the slope of this SSE curve, which is sum of squared residual or sum of squared error. So just we want slope, and how to calculate the slope or how to find the slope? Slope is given by this partial derivative. So that was the reason we do here the partial derivative. Our main goal was not to find the partial derivative, but our main goal was to find the slope. And whenever we just put this slope as 0, then we find the global minimum. So how to find the slope? So for finding the slope, obviously we required partial derivative. So that was the reason we did the partial derivative. So now let's do the partial derivative of this equation. So you can see at this expression we have the existence of omega naught, but only single. So what we need to do is, first of all, we need to apply the chain rule. So chain rule is nothing but, let me just take example, omega naught minus omega 1 x square. This is the upper equation, and now we are going to make apply of a chain rule over here. Let's do the chain rule, yi minus omega naught minus omega 1 x, and again multiply it with, let me show you, multiply it with again partial derivative of yi, the same terms over here, the same thing, yi minus omega naught minus omega 1 x with respect to omega naught. So what we are going to do here is, basically this is a chain rule. If you remember from previously, we need, that is, if I say something like p square, then the base that we are going to just that is do here the partial derivative, this p base should be same as the numerator. So in our case it was omega naught. So for that reason, if you do something like this, let's see here, if I just cut this part and this part, which is a basic multiplication, then we get the same equation over here, which is the upper equation. So we are not changing anything. Basically we are making sure that we can do partial differentiation correctly. So for that we are applying the chain rule. So this is nothing but a chain rule. We call this as a chain rule. So this is not going to make any difference on our equation. Any difference will not be made on our equation. You can clearly see this portion and this portion will be cut, and we will again find the same equation. But now we can do the partial differentiation with this equation by applying the chain rule. You can see the base, the equation over here. You can clearly see if I represent this yi minus omega naught minus omega 1 x as a square, and down we have with respect to a. So this is what we made here. Now let's do here the partial derivative. Now if you represent this, we just, if you do the partial differentiation of this, we just take this power down, which will be 2, and again we do, that is with the base, which is omega naught minus omega 1 x, and just subtract this 2 by minus 1. Now this is the derivative that I have talked about. So same as over here, you take this 2 down, 2, and we take this p and just do 2 minus 1, where in this case our p is this value inside this parenthesis. Now we did the partial derivative for this first part. Now let's do for the second part. Now yi here, yi, you can clearly see yi with respect to omega naught is a constant, so that means its value will be 0. So its value is 0, minus, now omega naught with respect to omega naught is a 1, because you can see derivative of p with respect to p is what we can cancel, and it becomes 1. So that means the derivative of omega naught with respect to omega naught is nothing but 1. And similarly, the derivative of omega 1 x is a constant, because there is no existence of omega naught over here, so that is also 0. So now if I multiply this the value, the outcome will -2, because this minus will be from here, and our equation becomes y1 minus omega naught minus omega 1x. So this is our equation of a slope. Now if I do equal to 0, then that means this will give us one global minimum on the curve, where our sum of squared error will be minimum. And we only did this in the case of omega naught. Now we also do the same task with the case of omega 1. We did this case for the omega naught, the same, and we find the slope, and it will be equated to 0, because in that point of the curve the slope will be 0. We do same with respect to now omega 1. Just in the case of omega 1, just replace this with omega 1 and do with respect to omega 1 here omega 1. And similarly this will be changed, a little bit will be changed, but in the case of omega 1 the equation will be quite similar, because in respect to omega 1 only this part will not be changed, this part will not be changed, only this part will be changed. In the case of omega we will have the x multiplied, because omega 1 is over here. So omega 1, if you do omega naught with respect to omega 1, it is 0. If you do yi, which is a constant, basically this will consider this as a constant, only the partial derivative of this will be valid, which is minus omega 1x. And whenever do the partial derivative of minus omega 1x, you get minus x. Now just multiply this thing with minus x, just multiply this thing with minus x, then you get the partial derivative of your curve with respect to omega 1, and just equate it with 0 also. So that means we have a two equations now. So if you just represent that two equation, you will find we will get these two equations. So these are the two equations that we get whenever we do the partial derivative with respect to omega naught and omega 1. And whenever we just find this value and equate it with 0, and this algorithm is nothing but our ordinary least squares. So this algorithm is our ordinary least square. What did it do? It basically found a global minimum in our curve. So it found this point, the global minimum, where the slope of this curve was 0. So that means if you want to find the slope, this was the process. Find the partial derivative for the slope, and we equate with 0. And these two equations can be represented in a mathematical form like this way. So if you represent these two equations, just equate with 0 and everything, then our previous two equations will be summarized by these normal equations where we have these things. And this is the basic implementation of linear regression. So linear regression is going to make a line in a way that our sum of squared error, that the curve of sum of squared error is minimum, which is by finding the global minimum. Our simple linear regression, or in fact any linear regression model, is going to create us this line finding this global minimum. Now from this equation, if you equate this equation, you will find the value of, that is, omega naught and omega 1. Just compute this equation, although we are going to use this equation in the upcoming lecture in order to solve some numerical. We are going to do in the tutorial session, we are going to solve this equation by hand and show you all the tasks. But now let's imagine we solve this equation and we got the value of omega naught and omega 1. So what is this value? Omega naught was nothing but the constant, and what was omega 1? It was nothing but a slope. Now we got the value of c and a m. So that means we can put this value of c and m in our equation, which is basically y equal to mx plus c. So we can make this formulation of the equation by just putting m in the place of omega 1 and c in the place of, that's omega naught. And now we will have some value, some equation, something like that. So we compute this equation, we get the value of omega naught, let's say 2. And we compute this equation again and we get the value of omega 1, which is, let's say, 4. Now you can clearly see we get the value of equation. This is what linear regression model will search. And we get this equation, and this equation is a model. Now this equation is a model which is nothing but a straight line. And here, by giving different input value, you can see by giving different x's, we can find this y. So that is our predictive model. So giving different value of input, we can now find different value of output using this straight line equation or using this model of linear regression. Now you can clearly see these two equations we got from nowhere, but with the partial derivative of these 2 points. And these two equations are basically the goal of these two equations is to find the lowest error. So that means it is an ordinary least squares algorithm is going to find the global minimum, and it is going to find this omega naught and omega 1 by finding the global minimum, which is basically minimum error. It will find minimum error by finding this omega naught and omega 1, and it is going to compute a model which is nothing but a linear regression model. And using that linear regression model, we can basically just predict different value for different input. So now let's take a simple example, although we are going to do the same tasks in the case of tutorial session. So the coming session will be the tutorial session, which we are going to compute our equations using ordinary least squares algorithm. But for now, let's see, we have these x and y for different points. So you can see for each and every points we compute the value of xi. So xi here is just add these points. So whenever you add this 1 plus 2 plus 3 plus 4 plus and everything, this value would come as 43. So we just compute this 43, and just basically what you do is this, for this x square, what you do is just take the square of x. So for this one, just take a x square, so it will be 1 square for the first one, and for the second one it will be 2 square, and take the sum of it, all the sum, and for this third it will be 3 square. So first of all, take the square of each of these x's and just add it, and you get this value. And similarly, just add all the y's, all the value of y over here, and you get 102 value, which is nothing but this yi over here. This summation basically means do for all these points. And similarly, just do y square compute. First of all, compute the y square and then do the summation. So that means compute the 7 square, compute the 8 square, compute the 9 square till this 13 square. Just do the same and just add all of it. Add all of it and you get this 1094. Similarly, the next thing is to multiply x and y. So just multiply this thing. 1 multiplied by 7 is 7. Let's see. So multiply this. 1 multiplied by 7 is 7. 2 multiplied by 8 is 16. And 3 multiplied by 9 is 927, and so on. So just multiply till the last and just add it. Then what you get is this value. So basically what this is saying is, first of all, do these tasks, what is inside, and then do the summation for each of them. So this way we get all this value. Now next thing, after finding all of this value, just compute this equation, the equation that we have here. See here, this equation. I told you, if we write this partial derivative equation into the mathematical form, we get this equation. So this equation, you can clearly see we computed this value, this value, this value, and this value, and this value also. So now what is n? So n is nothing but our total data points. In our case, if you take our example, our total data points was, so over here you take example, our total data points was 10 points. So 1 2 3 till 10. So we have 10 points total. So n value here is a 10 points. Now you compute all of these. See here, we have computed all of these. Now we can use that equation that we have created over here, this equation. So we computed this thing. So value of n is 10 for our this particular problem. Value of this is computed. This is also computed. This is also computed, and this one is also computed. Now we can clearly see we can get the value of omega naught and omega 1, because all of these values are known now. And now this omega naught and omega 1 will be computed just computing this equation. And after you find this omega naught and omega 1, they are nothing but y equal omega naught plus omega 1x. So let's say you compute some value for omega naught and omega 1x, then you get the straight line equation, which will be our linear model. Now let's do over here. So you compute everything, you put that equation over here, and you find the value of omega naught and omega 1 over here. So see here, you find the value of omega naught and omega 1. So you found omega naught value is this 5.19, omega 1 value is 1.19. Now our equation will become this. So this is what our that model is doing. Linear regression model is going to find this straight line, which will be our best fit line, because at this point our sum of squared error, which is basically just a way of saying error, is minimum, or we found the global minimum using this equation we computed the global minimum and we found this equation, and using this equation we found the maximum, the optimized value for slope and y-intercept, which is nothing but this omega naught and omega 1. And we found this equation, and this is the best fit line among multiple line. There might be infinite line. This is the optimal solution, and this is what linear regression aims to do. Similarly, to find this global minimum, there is another equation also if you want to try. So this y bar is the mean of y. So if you want to directly compute this omega naught and omega 1, not with that equation but with this equation, then you have this omega bar, that is x bar, and y bar. X bar here is a mean of x and y bar is a mean of y. So how to find the mean? So to find the mean, let's take an example of this x. So how to find the x bar? So here bar is nothing but a mean value of x and y bar is a mean value of y. So let me just compute y bar for you. So in order to compute the mean of x, just add all of these value of x's. So something like this: 1 plus 2 plus 3 till 7. So we have till 7. Just add all of these 4, 4, 5, 5, 6, 6 and 7 till the 7 and divide it by total number of points. So we count the total number of points: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 points. So this way we compute the mean and put the value over here, compute the y bar, put the value over here. And we don't know the value of omega 1. So how to find the omega 1? Omega 1 is a slope basically. So how to find the slope? So the slope over here is given by this standard deviation formula, which is this, you can see, standard deviation with respect to xy divided by standard deviation with respect to xx. And this equation you can compute by yourself, but in the upcoming lecture we are going to use this formula in the tutorial session and compute the equation which is y equal mx plus c, or which is y equal omega naught plus omega 1x, where this is another form is y equals c plus mx. So this equation will be computed by this technique in the tutorial session that we are going to cover in the next video. See you in the next one.